You might be saying this logistic regression we just did doesn't give us a prediction like, yes, you have this disease, or no, you don't have this disease. Instead, it gives us a probability estimate. But let's notice that that's actually more information than a simple yes, no. It gives us sort of a how certain are you that this person has the disease or not. It is common, but it's not required to convert the probability estimates from percents to a simple yes, no by just having a cutoff. For example, we could say any predicted probability above 0.63 is a positive test result, and below that is a negative test result. A common cutoff is 0.5 or 50%, but it doesn't have to be that. Turning a probability prediction into a specific category prediction is turning our soft classifier into a hard classifier. Let's go explore an Excel sheet that I've set up already that does this. So I've got the data set. I've converted it into what's called a data table in Excel that makes a lot of things nicer. So we've seen this data already. Here I'm computing a score by taking the M value, and I've named this cell. You can see up in the name box here, it has the name M value, so I can refer to it just with that name. And I've done the same for the C value. Um, so I'm saying take the M value, multiply by the chemical X value on this row of the data table, and then subtract the C value first, that's in parentheses, and then multiply by the M value. So we're getting all these scores. Score of 3.5 is relatively high, apparently. Score of -2, -3.5, those can easily happen. These are nice fractions, like they're all halves and integers because the data was rounded to the 50s. From that, we can compute the logistic function, 1 over the quantity 1 plus 2.718 raised to the negative score. And then here I've got some logic that says if our logistic probability thing was above whatever probability cutoff I have here, then give me the answer positive test, otherwise give me the answer negative test. And I've got that filled out for all the rows of the data table. And then we want to say, well, how well are we doing at accurately predicting people's results? So I'm going to summarize them in a two-way table. On the rows, we're going to have, does this person actually have the disease or not? And on the columns, we're going to have, did they test positive or not using our logistic function and our probability cutoff. So if someone doesn't have the disease and we report a negative test that says you don't have the disease, we're going to call that a true negative result. If they don't have the disease, but a test says they do have the disease, that would be a false positive. It's a positive, but it's false because we know in this data set they don't have the disease. The opposite would be a false negative when they do actually have the disease, but the tests missed it. Then there's true positives if they have the disease and our test says they have the disease. So I've got a fancy formula here called a pivot by, which is fairly new in Excel. It's like a way to do an automated pivot table that will update if you change the cutoff, for example. So here we're seeing 150 true negative results, 393 false positive results, 23 false negatives, and 434 true positives. It's not a bad idea to compute column totals there, like how many negative test results do we have, how many positive test results, how many people had the disease, how many people didn't have the disease in our data set, which could be different than in the actual general population. We can compute important things like the prevalence, the percent of people in our data set who have the disease, regardless of their test results. Um, this 2 by 2 table is called a confusion matrix because the off-diagonal things are kind of issues where we're confused about whether the patient has the disease or not, only because we know whether they actually have the disease. And you can read more about confusion matrices here. If you know hypothesis tests and statistics, you might have heard of type 1 and type 2 error. So we can say the type 1 error here is kind of like a false positive. Type 2 error is kind of like a false negative. But if you hadn't had statistics, don't worry about it. We can compute other important things like the false positive rate. So how many false positives did we have out of people who actually did not have the disease? We can also compute the false negative rate. There's things called sensitivity, specificity and sensitivity. Specificity is the probability that you test negative, given that you actually don't have the disease, which we would never actually know. But maybe there's like a gold standard test that we've applied to get the data we have. There's also sensitivity, which is also called recall, or true positive rate is the probability that you test positive if you actually have the disease. Again, which you never really know. So we want sensitivity and specificity to be large, hopefully near 100%. We want false positive and false negative rate to be low because they're false things. We can also compute something called negative predictive value, which is the probability that you don't have the disease if you got a negative test result, which is the opposite phrasing of sensitivity or specificity. There's also precision or positive predictive value, probability that you have the disease if you get a positive test result. So we want the predicted values to be large as well. We can compute the accuracy, like how many tests were actually accurate, divided by how many total tests did we give, which is true positives plus true negatives over all the combinations of true and false, positive and negative. And for this data table, that is the true positives and true negatives divided by the total number of tests. So it's 58% or so. Let's notice that there's no simple relationship like these things add to 100 between things like the false positive and false negative rate. 72 plus 5 is not 100. Between specificity and sensitivity, 27 plus 95 is not 100. Negative predictive value and positive predictive value, 86 plus 52 is not 100. So we can't go hoping for simple situations there. It is true that the false positive rate plus the specificity adds to 100, and the false negative rate plus the sensitivity adds to 100. There's another measurement called F1, but it has its own problems. It doesn't account for the relative badness of false positives and false negatives, for example. So when we're doing all this, there's all these different ways to measure the results that we just talked about. We should keep in mind what are the consequences of a false positive? What are the consequences of a false negative? For example, a false positive makes a patient worried until they get maybe a later, better, more expensive test that would say, oh, you actually don't have this. A false negative would mean we missed a disease and maybe we could have started treating it earlier. Maybe we'll catch it in a year, or maybe 2 years, I don't know. But it's going to be more expensive to treat, probably more side effects for treating a more advanced disease. The person could just be suffering in the meantime, not knowing that they have this disease. Maybe the disease itself causes suffering. And then how do we weigh the relative upsides and downsides of those things? So that's something that we should be talking about. And you should maybe set your cutoff so it kind of balances those things. So it's important to remember we can't reasonably expect a model to avoid all false positives and all false negatives at the same time. Even if your model achieves 0 false positives or false negatives on the data that you have, that's no guarantee that it will continue doing that on future data. And you should distrust anyone who promises you 0 false positives or 0 false negatives because that is too good to be true. And I've seen promises like that for various companies. Demanding a low false positive rate is very likely to increase the false negative rate and vice versa for the same set of input measurements. So we should have discussions with work colleagues, supervisors, government regulators, community members, and other stakeholders about the relative importance of false positives and false negatives. You might think about some of the issues that are just big in politics in the nation and the world these days, and think about how the various sides prioritize reducing false positives or reducing false negatives. One way out of the trade-off between false positives and false negatives is to take more types of measurements. Like we measured chemical X, what if we also measured chemical Y? Or maybe take better measurements, maybe measure chemical X 3 days in a row and take the average to reduce the noise or something. But that's more expensive. more testing, more blood samples, or it could be more time consuming, or both. So that itself is another trade-off that should be discussed with community members and everyone else. The balance between reducing false positives and negatives and more time and effort spent gathering other types of measurements. Another way out of the false positive, false negative trade-off is to use a better fitted or more complicated model on the same data that we have. That can be more expensive or time consuming in its own ways. It's more time spent by STEM researchers like you and me designing the model. It's more time and money spent training the model if it has more weights and biases to adjust, that computers take longer on it. And there's more time spent interpreting or figuring out what the more complicated model is doing and to what degree it's reliable. We might hope that gathering more rows of data, having more people in the data set, would be another way out of the trade-off between false positives and false negatives. It does help somewhat here, but it doesn't change the fundamental overlap in chemical X values between people who have the disease and people who don't have the disease. Gathering more rows of data here would give us a better estimate of the weight and bias to use in the model, which improves our predictive abilities on future data, but it might not improve both our false positives and false negatives on the existing data set. Some other ideas that are related. We don't have to have just one threshold. We could have two or more based on our model's probabilities, like low risk, low risk, medium high risk, and we could do different things for people in those different categories. We couldn't measure those in terms of false positives or negatives if we only have simple binary info on whether the person has the disease or not, but it might still be a good idea clinically. Everything I've said so far sounds like we have just one measure for the whole data set, like false positives across all people, all 1,000 people in the data set. But if we have subgroups of interest, maybe we should also try to quantify accuracy, positive rate, false positive rate, et cetera, in each subgroup to see how fair our model is, or maybe have a different model for each subgroup. That's controversial, though, sometimes, whether that's a good idea to have something like that, or especially different cutoff values for different groups. There are issues about having different cutoffs that induce lawsuits, and it's a big societal question that the medical community is dealing with, the legal community, all kinds of people. So like NFL concussion payouts, they apparently had two different scales, one for black athletes, one for white athletes. I forgot to demonstrate that if we change the cutoff, we'll see the false positive and false negative rate change. So right now I've got the cutoff set really low, 10%, and we have a fairly high false positive rate because we're giving lots of positive test results and a fairly low false negative rate. So if I set the cutoff to something bigger, maybe 0.6, then our false positive rate falls dramatically, but our false negative rate goes up. So, and we could even try a bunch of them systematically. Excel's not the best tool for that, but we could try it later.